Welcome to the discussion. Today we're diving into a fascinating paper titled The Homunculus Brain and Categorical Logic. It uses the abstract concept of a homunculus brain to explore how meaning is created through the interaction of syntax and semantics. Intriguing, right?
Absolutely. It's a novel approach to a very complex problem. The paper uses categorical logic, a powerful mathematical framework, to model the brain's processes of meaning making.
So instead of focusing on the intricate biological details of the brain, the authors create a simplified model. What's the advantage of this approach?
The simplification allows them to focus on the fundamental logical structures underlying the brain's function without getting bogged down in the biological complexities. It's a powerful. Think of a category as a collection of objects and the relationships between them. For example, a category could represent a set of numbers, with the relationships being addition or multiplication. A functor, then, is a mapping between two categories that preserves these relationships.
So in the model, neurons are represented as categories and the connections between them, the axons, are represented by functors?
Precisely. Each neuron is a category with its own internal logic, its own program. The functors model how information flows between these neuronal categories.
This is a very abstract model. How does it help us understand meaning creation?
The paper leverages the well-established connection between syntax, the structure of language, and semantics, the meaning of language, within categorical logic. They show how these two aspects are intertwined, not separate entities.
And this intertwining is modeled by a pair of adjoint functors, Lang and Sin. What do these functors represent?
Lang maps categories, neurons to theories, mental representations, while Sin maps theories back to categories. The adjointness expresses the mutual dependency between the syntactic structure of a theory and the internal logic of its semantic representation. They create each other.
So the brain's activity, represented by the network of categories, influences the creation of meaning, represented by the theories, and vice versa?
Exactly. The paper also explores the concepts of abstraction and realization. A theory represents a general concept, while its realizations are specific instances of that concept. They show a deep duality between these two aspects.
And this duality is also represented by a pair of joint functors?
Yes, a contravariant adjunction between realization and abstraction. This highlights how we can move between general concepts and their specific instances. It's a powerful way to model how we form and use concepts.
This is quite a sophisticated mathematical framework. How does it relate to the actual workings of the brain?
The homunculus brain is a highly simplified model. It's not meant to be a precise biological representation, but rather a tool to explore the fundamental logical structures involved in meaning creation.
So the authors aren't claiming that neurons literally are categories.
No, it's an analogy. The power of the model lies in its ability to capture the essential logical relationships, regardless of the specific biological mechanisms.
And the adjoint functors between brain and mind model the interaction between the brain's neural activity and the mind's creation of meaning?
Precisely. The adjointness of Lang and Sin implies a deep and dynamic interaction between the two categories. They shape each other.
This model suggests that the brain and mind aren't separate entities, but rather two aspects of a single integrated system.
That's a key takeaway. The model emphasizes the mutual influence and interdependence of neural activity and mental representations.
The paper also mentions previous work using logic and category theory to model the brain. How does this work differ?
While previous work has used category theory to model various aspects of brain activity, this paper uniquely focuses on the interaction between syntax and semantics in meaning creation, using the powerful tool of adjoint functors.
So it's not just about modeling individual neurons or neural networks, but about modeling the process of meaning making itself?
Exactly. It's a higher level model that focuses on the fundamental logical structures underlying cognitive processes.
The paper concludes by emphasizing the interplay between abstract mathematical structures and real-world processes. Can you elaborate on that?
The authors argue that abstract mathematical models, like the homunculus brain, can not only describe real-world processes, but also effectively act within them. It's not just a passive description, but an active interaction.
They use the analogy of a computer program generating a phase portrait on a screen. The program's instructions are analogous to the brain's internal logic, and the resulting image is analogous to the creation of meaning.
Precisely. The abstract model provides a framework for understanding how formal structures can produce real effects in the world, including the world of our minds.
This is a very ambitious undertaking. What are some of the limitations of this model?
The model is highly simplified. It abstracts away many crucial details of the brain's biological structure and function. It's a starting point, not a complete picture.
And the assumption that neurons can be modeled as categories is a significant simplification.
Absolutely. The model's value lies in its ability to highlight fundamental logical relationships, not in its biological realism.
So it's more of a conceptual framework than a precise biological model.
Yes, it's a conceptual framework that offers a new perspective on the brain-mind problem. It suggests avenues for future research, exploring the interplay between abstract mathematical structures and cognitive processes.
What are some of the potential future research directions stemming from this work?
Further development of the model, incorporating more biological detail, exploring different types of logic, and investigating the implications for artificial intelligence are all promising avenues.
This model could potentially inform the development of more sophisticated AI systems?
Absolutely. Understanding the fundamental logical structures underlying meaning creation could lead to the development of AI systems that are more capable of understanding and generating meaning.
It's a fascinating connection between abstract mathematics, cognitive science, and artificial intelligence.
Indeed. The paper bridges these fields in a novel and insightful way.
The paper also discusses Tarski's work on truth definitions and the role of meta-language. How does this relate to the homunculus brain model?
Tarski's work provides a formal framework for defining truth within a language. The homunculus brain model builds on this by showing how the interaction between syntax and semantics, as modeled by adjoint functors, can lead to the spontaneous emergence of meaning. It's a more natural and dynamic approach than Tarski's metalanguage approach.
So the adjoint functors provide a more elegant and powerful way to model the relationship between language and meaning.
Precisely. It's a more integrated and dynamic model that captures the mutual influence of syntax and semantics.
This discussion has been incredibly insightful. Thank you for explaining this complex topic so clearly.
My pleasure. It's a fascinating area of research with significant implications for our understanding of the mind and the development of artificial intelligence.
That was a great discussion.